Hello everyone, this is Mr. Teen Tutor here, and today we will be talking about the fundamental theorem of calculus. Now, as you can tell from the name, this is one of the most powerful theorems in calculus, and here's why. Unlike methods such as the Riemann sum and the trapezoidal sum, this theorem is going to algebraically give us the exact value of the area under the curve. So rather than estimating what the area under the curve might be from point A to point B, the fundamental theorem of calculus will give us the exact value, and that's through anti-differentiation. So based on that, obviously, if you look at this right here, big F prime of x is equal to f of x here on the inside. So let's do an example problem. So say we want to find the area under the curve x squared from 0 to 2. Now, when it comes to the fundamental theorem, you don't have to draw a picture necessarily. But let's just draw one anyway, just so we can see what's going on. So obviously, when you plug in 0 for x, you get 0, so that point's right about here. And then when you plug in 2, you get 4, so we'll just say that point's right about here. So here's 4. And 2's right about here. So we are trying to find the area under the curve from 0 to 2. So we're trying to find this area right here. So when it comes to Riemann sums or trapezoidal sums, it's useful to draw a picture because you will need to do that in order to effectively use those methods. But with the fundamental theorem of calculus, you don't have to draw a picture. So let's just go straight to it. So we know what f of x is, we know our a's and b's, so let's see what we have. So remember, a is less than b, so the lower value goes down here and the upper value goes up here. So 0 would go here, 2 would go here, x squared dx. Now here's something to keep in mind. In this example problem, we are looking at x squared, and we're looking at the values from x equals 0 to x equals 2. This differential does not necessarily have to be dx. It could be dy, but it'll be dy if we are changing the perspective and looking at it from y. But as you can see right here, we're not looking at it from y, we're looking at it from x. So remember that. This doesn't always have to be dx. It depends on the type of problem. If you're looking at it from the y perspective, so like let's say you're looking at it sideways, so this would be like a, well, it'd be sideways parabola, but in reality it would be, if you were to take the square root here to isolate x, you would have the square root of y equals x plus or minus. Well, then in that case, you would be finding this area. And so then you would be looking from 0 to 4 because you're looking along the y-axis. But that's not the case here. So we're looking from 0 to 2 because this is from the x perspective. So keep that in mind. So then that means here we have big F of 2 minus big F of 0. Now, in order to find big F, we need to integrate this. So let's just pretend that the 0 and the 2 are not there. Let's just treat this as an indefinite integral. And so when we treat this as an indefinite integral, we come down here and we get 1/3 x cubed. Now, of course, when you're doing the indefinite integral, you need to put the plus c. But when it comes to definite integrals and finding areas under curves, the c's are irrelevant because the c's actually cancel out. So if we want, we can just do c minus c here. And then this notation here basically says, here is my antiderivative, and I want to find big F of 2 minus big F of 0. That's what this line here tells us to do. So let's do exactly that. So we get 1/3 times 2 cubed minus 1/3 0 cubed. So that's 8 times 1/3, so that's 8/3. 0 cubed is 0. 0 times 1/3 is 0, so 8/3 minus 0 is equal to 8/3. And because we're determining the area under the curve, it's good to put units squared. So there you go. this value right here, 8/3, is the exact value under the curve from 0 to 2. That is this area right here in this little drawing that I have. Now, when you use Riemann sums or trapezoidal sums or any other method like that to find the area under this curve, you might get a value that's close to 8/3, but you won't necessarily get 8/3 exactly. So when you're doing problems like this, it's always good to see what the fundamental theorem spits out. This is the exact value right here, and then you can use this and compare it to the values you get when you use Riemann sums or any other methods like that. So again, that's another way how the fundamental theorem could be useful. But overall, as you can see, very powerful theorem. If you've done Riemann sums, you know that from time to time they're tedious, they take a lot of work. But with the fundamental theorem, assuming obviously the problem's a little not too complex like this, you can go right to the answer. So there you go. This is the fundamental theorem of calculus. I hope you enjoyed it.